Welcome to the second acid and bases video tutorial covering the concepts related to pH. This picture should be familiar to you. It of course is the colour chart for universal indicator, showing the relative pH numbers associated with the different colours. The purpose of this video is to look more closely in detail at what pH actually is and what the words acidity and alkalinity mentioned here actually refer to, and how they are linked to this pH number. In this video tutorial, our outcomes are to review foundation ideas about pH, to define the mathematical relationship to calculate pH, to carry out calculations of pH on acidic solutions, to describe the dissociation of water as an equilibrium reaction, and to use the equilibrium constant of water, which is called Kw, to find the concentrations of hydronium ions for an alkaline solution, which of course then means we can calculate the pH of an alkaline solution. The first of these learning outcomes are important at an achievement level. These last three are more important at a merit excellence level, as the concepts covered are deeper in understanding. What do you know so far? Let's review some of the ideas you should already know about pH. You should know, of course, that pH values range from 0 to 14. You should know that pH value can be found using an indicator, like universal indicator, or using pH strips, or even a pH meter if one is available. You should know that pH is a measure of how acidic or alkaline a solution is. Or you might know that pH measures the concentrations of hydronium or hydroxide ions in a solution. These are common descriptions of pH, but only the last one comes close to a definition of what pH is. The correct definition of pH is this: pH is a measure of the hydrogen ion concentration in a solution, where the H stands for hydrogen. Let's look at some key terms first. Acidity. This, of course, is a term that describes how acidic a solution is. That is, how concentrated the solution is in hydrogen ions. Another, perhaps less common term you would have used is alkalinity. This, of course, describes how alkaline a solution is. In other words, how concentrated the solution is in hydroxide ions. Let's think a little bit about grammar at this point. Acidic and alkaline are adjectives, and acidity and alkalinity are nouns. That means you describe the solution as being acidic or alkaline, or you describe the acidity or alkalinity of the solution. It is important to choose the correct form of the word if you're writing a written description. Now let's look at a key term related to solubility. You may or may not know all acids dissolve in water, but not all bases do. The bases which are soluble are called alkalis, like sodium hydroxide, ammonia, and baking soda. Insoluble bases include substances like copper oxide and calcium carbonate. These don't dissolve in water, but will dissolve, of course, in acids, because this would be a neutralization reaction. Now let's delve deeper into the concept of pH. And note, it must be a lowercase p and an uppercase h. Firstly, pH is not an abbreviation. What it is a representation of a mathematical relationship given like this. pH is equal to the negative log of the concentration of the hydronium ions, which is shown by this formula. Now is a good time to point out that H3O+, which is the hydronium ion, is the same as H+, the hydrogen ion. They are indistinguishable, and you may use one or other as you see fit, but H3O+ is technically more correct. So pH is a mathematical formula. pH is a way of representing a wide range of numbers on the base 10 scale. That means all numbers ranging from 1 down to 10 to the minus 14, and representing them on an easy whole number scale. You will learn more about log scales in advanced maths, but essentially each whole number on the log scale is a factor of 10 on a decimal scale. So changing very, very large or very, very small numbers into a log scale makes them much easier to deal with. The P in this equation stands for potential, which really means negative log. So pH is a measure of the hydrogen potential, i.e. the negative log of the hydrogen concentration. Now here's something that might do your head in. You could also have POH, which would be a measure of the hydroxide potential, that is, the negative log of the hydroxide concentration. Looks a bit unfamiliar, but in fact this little relationship can be very useful once you learn more and more shortcuts using pH. So we can have lots of different P's, but pH is the one that you're most familiar with. Let's now look at an example of how you could use your calculator correctly to input a pH calculation. Here's an example. What is the pH of a solution if the hydrogen concentration is 0.1 moles per litre? How would we input that? Well, you would do something like this. So using these buttons on your calculator, you should pause the video at this point and attempt the calculation yourself and see if you get the same answer as me. The answer I get is 1.0. So the pH of a 0.1 molar solution of hydrogen ions is of course a pH of 1.0. This is also a good time to point out that when you are writing the answer to a pH calculation, you should be quoting at least one decimal place in your answer. Preferably no more than 2 or 3. Okay, let's look at some worked examples of how to calculate the pH of an acidic solution using our formula for pH. First question, what is the pH of a 0.001 mole per litre solution of hydrochloric acid? We're going to break this down into some few basic understandings. Firstly, hydrochloric acid dissolves completely in water in a 1-to-1 ratio. So what we need is the concentration of the hydronium ions. So in this case, the concentration of the hydrogen ions will be the same as the concentration of the acid. In other words, 0.001 moles per litre. Now we know this, we can calculate the pH. Negative log 0.001, and if you input that into a calculator, you should get a pH of 3.0. Let's look at 2 more questions. Question 2. What is the pH of this concentration of hydrochloric acid? Same acid as before. The concentration of the hydronium ions will be the same as the HCl because that dissolves and dissociates in a 1-to-1 ratio. So the hydrogen concentration is the same value. Once we know that, we can calculate the pH. Now you should definitely try inputting this one into your calculator to make sure you are using the correct functions. You should be using the EXP button to put the exponent form in. Your answer you should get is 5.13. Make sure that you do. The third question has an extra complication in it and something we'd just like to point out so that you're aware of this. In this question, we're asked to calculate the pH of a sulfuric acid solution. What we need to be aware of that when we dissolve sulfuric acid, it dissociates in a 1-to-2 ratio. So the hydrogen ion concentration will be twice as big as the concentration of the acid. So 0.004 moles per litre. There are 2 hydrogens for every acid molecule that dissociates. Once we're clear on this, we can calculate the pH. And we should get an answer of 2.4. Now we need to deal with the inverse. How do we calculate the concentration of a hydrogen ion in the solution if we know the pH value? And this is how we do the reverse calculation. If we read this out, it would say the concentration of the hydrogen ions is equal to the inverse log of the negative pH. On your calculator, you would input this as shift log function. In other words, the inverse log. Let's try an example. This will help you. What is the concentration of hydrogen ions in a solution that has a pH value of 4.5? So on your calculator, you need to input the calculation using these buttons. You should pause the video at this point and attempt this calculation yourself. Hopefully, this is the answer that you got. 3.16 times 10 to the minus 5 moles per litre. Note that this answer is a concentration, so of course it must have a unit. You will need to practice and remember how to using these relationships. We'll be doing some of this in class. You won't get given these formulas in your exam, They are simple relationships that need to be remembered. You should pause the video at this point and write these two relationships down onto your whisk sheet. You will need to practice using them so that you get confident. Okay, time to delve a bit deeper. This is definitely aiming towards higher grades. We need to delve a bit deeper into pH so that we can deal with alkaline solutions like sodium hydroxide in order to calculate their pH. But before we do this, we need to pause and consider a closer look at pure water, which is an amphiprotic substance. Water reacts or dissociates itself in an equilibrium reaction according to this equation. Simply put, when water molecules collide with each other, some react in this way. One water molecule acts as an acid and another water molecule acts as a base. This is its amphiprotic nature, transferring a proton from one water molecule onto the other in an acid-base equilibrium reaction. And since this is an equilibrium reaction, we can write an equilibrium expression for it, which would be this. And, given an equilibrium, there would be an equilibrium constant, which is this. And this is often referred to as the dissociation constant of water, Kw. This is a fixed value at 25 degrees centigrade. Note that the value of the equilibrium constant is very small, so that the equilibrium position lies to the left, in other words on the reactant side, and the amount of dissociation of water molecules to ions is extremely small. In fact, really, only 1 in every 10 million water molecules dissociates in water, so it's not very significant. You will need to remember this relationship and its value, as it will not be given in assessments. You should pause the video at this point and also write this down onto your whisk sheet. Okay, let's look at a graphic that will help you see the relationship between hydroxide ions and hydronium ions in water. And remember, this applies to any water solution, so all of aqueous chemistry is related to this. It's very useful to see the relationship between hydronium, hydroxide and pH. There's a copy of this in your graphic in your workbook, so I'll just try and give you some guidance on how you can use it. As the concentration of the hydroxide increases along this line, for example by adding sodium hydroxide, the concentration of the hydronium ions decreases. And this of course is to keep the value of K the same at 10 to the minus 14 and satisfy Le Chatelier's principle. And if we take a position here, you can see that the hydronium concentration is very small, the hydroxide concentration is very large. Together they will multiply to give the value of 1 times 10 to the minus 14. Let's have a look at what happens at pH equal to 7. The concentrations of the hydronium ions and hydroxide ions will be equal, obviously because the solution is neutral, and they will both be 1 times 10 to the minus 7 moles per litre. We can show this by applying a bit of algebra to the equilibrium expression here. At pH 7, the concentrations of the hydronium ions and hydroxide ions will be equal. So therefore, to calculate one of them, you just need to square root the equilibrium constant. And of course, if you want to know the pH, you just negative log this number, and you will of course get a pH value of 7.0. Okay, what happens if we lower the pH of the solution by dissolving some acid? Let's say to a value of about 4.0. When you have a pH of 4.0, your hydronium concentration will be shift log negative 4, which is 1 times 10 to the minus 4 moles per litre, which will be here on your graph. So that will give you the concentration of the hydronium ions. What will happen to the concentration of hydroxide? Well, it will have to go down significantly in order to keep the value of the equilibrium constant the same. We can calculate that using some algebra. So the hydroxide concentration will be 10 to the minus 14 divided by the hydronium concentration, which will give us a value of 1 times 10 to the minus 10 moles per litre. So as the hydronium concentration increases by adding some acid, the hydroxide ion concentration has to decrease in order to keep the value of the equilibrium constant the same. Simple Le Chatelier's principle, really. Now, here is something to remember. To work out the concentration of the hydronium ions in a solution, you take the equilibrium constant value, 1 times 10 to the minus 14, and divide by the hydroxide concentration. You should probably pause the video at this point and copy this rearrangement down onto your whisk sheet, as it will be one of the most useful ones to you if you're struggling to apply difficult concepts. Let's look at some calculation examples to show you how to use this value in order to calculate the pH of an alkaline solution. First one, how do we calculate the hydronium concentration of a 0.001 mole per litre solution of sodium hydroxide? Well, firstly, we need to be aware that there's only one hydroxide ion in sodium hydroxide, so the concentration of the hydroxide ions will be the same as the sodium hydroxide, in other words, 0.001 moles per litre. Now we can apply our rearranged dissociation equilibrium of water, 1 times 10 to the minus 14 divided by the hydroxide, gives us the concentration of the hydronium ions. Of course, it's a concentration, make sure you include a unit. What is the pH of a 0.01 mole per litre sodium hydroxide solution? Well, the first step is to calculate the concentration of hydronium ions. And we did that in question 1 already, so we've already got it. Now that we know this, it's a simple matter of putting it into our pH calculation, and we'll get a pH value of 11.0. Here's a doozy. What is the concentration of hydroxide in a solution with a pH value of 8.9? How do you deal with this? A little bit harder now, let me show you how. First, you need to take the value you do know, which is the pH value, and apply the inverse relationship to calculate the concentration of the hydronium ions. So shift log negative 8.9 gives you the concentration of the hydronium ions of 1.26 times 10 to the minus 9 moles per litre. Once you know this, we can go back to the dissociation equilibrium constant for water, rearrange this to give us the hydroxide concentration. So 1 times 10 to the minus 14 divided by the hydronium concentration gives us our answer of hydroxide. So you'll need to be able to manipulate our three relationships to be able to answer any question that you are given. One more. How would you deal with this challenging example? If you dissolve 4.5 grams of sodium hydroxide in 500 ml of water, what would be the pH of the solution? You should pause this video at this point and see if you can tackle it. It's quite a tricky one. How would you even start? In order to give you a hint, a molar mass has been provided. So how do you think you'd best use that? Once you've had a go, by playing the video at each step, the calculation process will be uncovered. So if you need a hint, here's the first one. Right, do you need another hint? Here's another one. Think you can do it now? Here's another hint. And to get the final answer, you do this. This would be a very difficult calculation if given in an exam. There are 4 calculation steps required to get the answer. So if you got 13.7, you'd probably be given an excellence. So that's it. If you were paying attention, you would have learned that pH is a mathematical representation of the concentration of hydrogen ions. You would have learned how to calculate the pH of an acidic solution, how to calculate the hydronium ion concentration of solutions with a given pH. You would have learned that water dissociates in an equilibrium reaction and has a dissociation constant called Kw. That we use the Kw to find the concentration of hydronium ions in an alkaline solution, and then how to calculate the pH of an alkaline solution. A lot of learning intentions in one video. Don't forget these relationships. You will have to remember and know how to use them. You should all have these relationships written down onto your whisk sheet. pH calculations often take practice, so give yourself some time to practice the examples in class and in your workbooks. In the next and final video for this topic, we will look at the concept of strong and weak in terms of acids and bases. See you then!